get started. This is just finishing up the second part of phonons, and in this lecture we're going to now generalize to two atoms in our unit cell rather than just one atom. But first of all, we'll just finish off some things that were left over from last lecture. So let's try and remember. We had obtained our dispersion curve, remember? It looked like this, and 0 to 2 pi and a is obviously a reciprocal lattice vector, and we were restricting ourselves to the first Brillouin zone because this thing's just periodic. This working is just showing you or demonstrating that the dispersion curve is periodic. Remember, we had the solution of this form, some amplitude a e to the I omega t minus I k n a, where a was the lattice constant, if you like, and n is an integer. So if we substitute k being equal to 2 pi n a, which we know is our reciprocal lattice vector, and you follow that working through there, and you find you get this term here, which just goes to 1. So you basically end up with exactly the same expression, namely this form of the wave, which is what we started with. Okay? So this is what we see here, this periodicity. And we've seen this before from our electronic bands. You know, if we have in real space just this one-dimensional lattice, atoms at A, 2A, minus 2A, then we'll have reciprocal lattice vectors correspondingly at minus 2 pi n a, minus 2 pi n a, and positive 2 times 2 pi n a, and so on. So that's just formalizing and proving that we have this periodicity. Okay, another thing, remember from our electronic band structure we could define also the phase velocity and the group velocity. We can have the same thing here for our phonon, or our phonon dispersion curve, if you like, our acoustic curves, where the group velocity, just as before, is defined as the derivative with respect to k. Okay, so you can see that at the point here it will go to 0, the group velocity. And the phase velocity is defined to be just omega over the particular k that you are at. And in the limit that you have a very linear dispersion like you've got here, these two velocities will just be equal to each other. So group velocity and phase velocity. Okay, this just shows some other kinds of dispersion curves. This is the one we have just talked about here. Vibrations in a one-dimensional chain has this kind of characteristic linear form here near for small k. Then we had, you know, earlier our energy, h bar squared k squared on 2m, and the corresponding frequency omega is just can be written as h bar k squared on 2m. And it also has its dispersion curve here, omega versus k. Here it's got this parabolic shape. And another example could be, for example, here, light in vacuum. Here you've got frequency times wavelength equals the speed of light there. And you can rearrange that also into a form of omega equals kx, where omega is a function of k. And you can see if you plot it as a function of k there, you just get the gradient being c. So this is a dispersion curve for light in vacuum. We know that we also can have light in some kind of matter, and in that case we get a corresponding dispersion curve, but in that case we don't know exactly c. It's dependent on actually the frequency. So I haven't got a plot for it, but it will be non-linear because c will actually depend on the omega. But I just put that there as another example. Okay, so now comes to another important aspect, which I think will be okay for you because we have done it just before in the electronic structure. For electrons in solids, you know, we've got this nice curve here, but it only is valid for certain discrete values of k, just like before. Okay, so we're going to just see what those values of k are. So k is quantized, and it depends on how many atoms there are in our chain. Remember, just like before we had our solid, it depended on how many unit cells we had in our solid. So this is our chain. For example, we've got n atoms. These are the periodic boundary conditions that we are going to use. They're called Born-von Karman boundary conditions. So if you've got your function here, okay, basically what it says is that if you go around to the n atoms and you come back to 1, you will get the same result at n plus 1 or just 1. Okay? So whether we are n, the total number of atoms in your solid, plus the little n we are considering, it's just equal to that one. So that allows us to describe a system where the waves don't have to be standing waves. They can be traveling waves. So these are the boundary conditions. Now, I'll spend a bit of time on this, but I think you'll all get it fairly fast. So these are the boundary conditions as I explained. As usual, we have the distance between the atoms being called A. Okay. Now, we had our function here. Remember, we defined it as some amplitude e to the I omega t minus k I k n a. So we need to have it satisfied that if you substitute little n for n plus the number of atoms in your system, you'll get the same answer. Okay, so substituting n plus big N for little n, this is our usual expression. Now substituting n plus little n, we can rearrange and get that thing. And you can notice that the term here on the right-hand side is exactly equal to that, which is what we want, because once we've gone completely around the circle, we want to be having exactly the same form of the function. So this term here must go to 1. Okay? So we must have e to the I k n a equal to 1, and that will occur if k has values 2 pi p, where p is some integer, over big N times a. And remember, just as before, we call L the total distance. Before we had it to be the total distance, length of our solid, and here we have it to be the total distance around the chain. So N times A equals L. So, okay, what does that tell us? It tells us that we can have n, big N, k points or k values, okay, where n is the number of atoms in your solid. And we know that our reciprocal lattice vector, or the range of k, is 2 pi on A, you know, for the periodicity of our unit cell, if you like. And we now know that we have n allowed values of k, and the spacing of them is 2 pi over L. So just like we did, I think it was for assignment 6, you can just work out how many modes you're allowed to have by dividing 2 pi on A by the spacing of those k vectors. And you get n. Just like before when we did the electronic structure, the number of allowed k points was equal to the number of cells we had. For this one-dimensional system, it's also equal to n. In this case, n is the number of atoms or unit cells of our system as well. So the K points are discrete that we are allowed to have. This shows an example with 10 unit cells or 1 atom per cell. Right here, 10 unit cells, 1 atom per cell. So in this example here, our G vector, reciprocal lattice vector, goes out to 2 pi before it repeats, and back in the other direction. And the Brillouin zone is just that part of interest that repeats only once, does not repeat, this part here. And because we have n equals 10, the spacing of the K points is 2 pi over 10a. So each of these little spacings where the K points are is 2 pi over 10a. So for this system that's only got 10 atoms in the chain, we can just plot the points here. Okay? A line has just been drawn to guide the eye. So what's the main takeaway? N atoms give n so-called normal modes of vibration. Okay? N atoms in your chain gives you n values of K, and correspondingly n values of omega. And if you have a very long chain, you can imagine that the K points get very, very dense. Okay? So that's for 1 atom in your chain. So it's helpful to kind of write it down. This is, again, for 1 atom. This will be for 2 atoms. So a chain with 1 atom per cell and n unit cells, we get this many modes, okay? We get n, where n is the number of cells, and you can say times 1. So we have 1 atom in the unit cell. Okay, now if we consider 2 atoms in the unit cell, how many modes do we get? Okay, we still have n unit cells, okay? But we've got 2 atoms in the unit cell, so you'll get 2 modes. So for 2 atoms in the cell of this chain, we have 2n degrees of freedom and 2n modes. And so this is basically kind of what you would get if you had 2 atoms in your unit cell. You get this mode down here, which is called the acoustic mode, and you'll get another one up here, which is called the optical branch. And you can see now that for a given K value, you get 2 possible frequencies. Okay, 1 here and 1 here. This one, you get 1 here and 1 here. Okay. At this point, it's probably good to make contact with sort of the phonon, the quantum mechanics picture here. So what do we have for the classical situation which we have been dealing with? If we have a normal mode at a certain frequency, like from our plot, okay, we had a K point, a corresponding frequency, then the corresponding quantum system will have the following energies here. So this is our omega, which we get from our phonon plot, if you like, before. But in this case, we will get many different energy levels where n is an integer. Okay. So, and these spacings here for the different excitations, first excitation, second, third, fourth, and so on, is just h bar omega. So, and we call these phonons. Okay. So clearly the ground state is when n equals 0, and it has a corresponding 0 point energy here. If you put that goes to 0, then you have a 0 point energy. And people often calculate the 0 point corrections to, if you're doing, say, quantum mechanical sort of simulations of materials, that's usually carried out at t equals 0, but you can somehow correct for these 0-point energies by calculating just the vibrational energy as a function of position. Okay, I think I've said that. So that's kind of the corresponding picture. This might illustrate it a bit better. So here you have your kind of curve that we've got before. For various k's, you get certain frequencies. So for example, if we are here at the first k point, small value of k point over here, then h bar omega, the spacing is going to be small for the various excitations. And if you are further here in the Brillouin zone, your excitations are going to have larger spacing. Okay. I think that's all we're going to talk about for the connection between the quantum model. But what we're going to turn to now is our unit cell with 2 atoms in it. So it's kind of the next level of complication, if you like, from our one-dimensional model. So, okay, what have we got? We've got 2 atoms shaded different colour, M1 and M2, with spring constants K1 and K2. Obviously, you can draw the unit cell however you like, this way or this way. And in what we're going to do here is take M1 equal to M2, but keep the spring constants different, K1 and K2. One could also do it the other way and get slightly different results if you have different masses and keep the spring constants the same. I don't think that's on your assignment, but that could be a good thing to have next year, perhaps. Okay, so remember when we were first describing the one-dimensional chain, we had an equation very much like this, except we had the same spring constants, okay? In this case, we've got 2 different sorts of atoms, so we've got 2 different spring constants, and, okay, X and Y, they just label the positions of the different species of atoms, okay? So if I'm at position X here, delta Xn, say, I am interacting with Y of n via spring constant 2. And I'm also interacting with Y minus n minus 1, which is Y1, via spring constant K1. Okay? And the same thing for, say, this one here, interacting with this one and this one. And if we assume the same kind of solutions as before, as written down there, with our amplitudes AX and AY, then we're going to just substitute those into these expressions. Okay, I don't think we've already mentioned that. Okay, so all that's been done there is substituting in for the solution, okay, into here, into here, into here, into here, into here. Just substituting in. You can get cancellation of some of these exponential terms. For example, this one will cancel with this one, and will cancel with this one, and so on. And when you go through and reduce your equations down a bit, you obtain these expressions here. Okay? And you can recognize that you can write this as an eigenvalue equation here with eigenvectors AX and AY, AX and AY. And then one can solve that by finding the zeros of this determinant. Okay, so we're just taking the m omega squared over this side and going to find the zeros. Okay, this time this usual procedure. So what happens you boil it down to this expression here. You get a plus and a minus because you are taking the square root of the magnitude squared. And so this obviously gives you two kind of solutions, okay? Focusing on this second term here, this is just evaluating this a bit more, making the magnitude, take the complex conjugate, multiply it by itself, take the square root, and when you do that, you obtain this expression here. So, you know, if it was me, I would be going through this and making sure everything makes sense. You know, get your hand out and start deriving it. Just make sure it all fits together. Let me know if there's an error, but there shouldn't be. Okay, let's go on a bit further. So, basically you will find an expression for the frequency here, plus or minus square root of this horrible thing over here. Okay. As I mentioned before, the upper band that you will get is called the optical branch, and this lower branch is called the acoustic branch. So what we'll just stop a little bit and work, just derive those these things a little bit together, just to slow things down and see how it comes about. It's very straightforward, I know. Nevertheless, let's do it. Okay, so this is what we've got here. So if we look at the acoustic branch down here, we can see, well, firstly, if you look down here, we have for k equals 0. Well, we've got to check, does omega equal 0? Is it correct? Yes, it is, really. Because you'll end up, the acoustic branch, we take the minus of the choice there. So you'll just end up with omega minus square root of kappa 1 plus kappa 2 over m, taking the minus, and square root over m. And remember, k is going to 0, so this term here will get you, 1. And then you'll end up with just kappa 1 plus kappa 2 all squared over m. And these two will just cancel out. And so, indeed, as we would hope, it describes that well. Okay, so what about for k equals pi over a? We can do the same thing, again for the acoustic branch, and we get omega minus, in this case, kappa 1 plus kappa 2 on m minus 1 over m square root of kappa 1 squared plus kappa 2 squared. And here we put cos of pi on a times a. That will just be minus 1. So we get minus 2 kappa 1 kappa 2, which, as you can see, kappa 2 on m minus kappa 1 minus kappa 2 all squared on m. And I've got a square root in there as well. So you will get cancellation of kappa 2, and you'll be left just with the square root of 2 kappa 1 over m. Okay, so that's all you're doing to get these values here. Oh, yes.
What could not be like kappa 1 cancelling out?
Uh,
Have that in the square.
here.
It could be kappa 1 minus kappa 2, or it could be kappa 2 minus kappa 1 squared.
I'm not sure where you're looking at, but you're probably right. But
You have kappa 1 minus kappa 2 squared in there.
kappa 1 minus kappa 2.
At the
Oh,
square,
here.
correct, yeah.
Yeah.
Doesn't become minus
Oh.
1 and then plus kappa 2.
So you're thinking this should be kappa 2?
Oh, I'm not saying that.
It could be. Well, there's your kappa 2 up there. Okay. Yeah. What you're saying is, how do we know it's not the other way around? Well, I guess if you just follow the working from here.
That thing gives you like kappa 1 minus kappa 2 or kappa 2 minus kappa 1.
Yeah, that's a good point. That's a good point. Yes, that's a good point. I think you do. Yeah, like the way it will turn out. You know, they're just, yeah, basically I guess the same, and whichever's value of kappa is lower will be the lower one. Yeah, and I think the same thing. So for the optical one, you can just do the same thing, which I won't necessarily bother going through. So you can consider k at pi on a, just like we did. And as you said before, you will just get the opposite there. And whichever one's low will be the one you get at the gap there. And one can consider k going to 0. And yeah, just finding out, you get there omega plus being equal to the square root of kappa 1 plus kappa 2 over m plus 1 over m kappa 1 plus kappa 2 all squared, and then you get the square root of 2 kappa 1 plus kappa 2 on m. Okay, so that kind of makes sense there. Fine. Fine.
Can I ask you just a question? The two-branch, optical and acoustic,
Yes?
because we're working with a diatomic atom, right?
Right.
And so we have two atoms, and they can both be, I don't know how to describe it, both be part of the acoustic branch and optical branch, or?
Yeah, that is coming. That is coming because once we get the solutions, then we can see actually how the vibrations look. Yeah. Okay, so what we should do now is, if we consider very small values of k in our dispersion near the origin, if you make the small angle approximation here for cos of Ka, which is 1 minus a half Ka squared, and substitute it in here, then you can find for this acoustic mode here, the one that's very linear, that it can be related to the sound velocity. Remember we calculated the sound velocity earlier, or showed the equations for that? When you do that for this acoustic branch near k going to 0, small angle approximation, you obtain this. And you can see that it's at the same form as the sound velocity, where instead of having just the value of the spring constant, we've got this so-called effective spring constant here, K1, so kappa 1, kappa 2 over kappa 1 plus kappa 2. Okay? And the density of the spring in this case would be 2m, twice the mass divided by A. So it's of the same form. Okay, so coming to the question of what the modes actually look like. Remember we had the eigenvalue equation up here. This is just from what we had before. You can just rewrite it like this expression here by pulling out common factors here, putting the m underneath there. And you can see that you'll get a solution when ax and ay are both equal to 1. That is, if you substitute ax and ay to be 1 and 1, this will hold. So these are the solutions. And so remember, the a's are the amplitudes of the vibrations. So it tells that for atom 1 and atom 2, they're both positive and both the same magnitude, so the atoms move in the same direction, okay, like that, for the acoustic mode. When we do the expression for the optical mode, remember the optical mode is up here, and the corresponding equation just from before is up here. If we consider at this point here k equals to 0, what we can find is that the eigenvectors that solve this expression here are then opposite. Okay, so the motion of, say, the first atom, AX, will be in the opposite direction to the second atom. So in the acoustic mode here, the atoms are vibrating against each other. Okay. This is just to show, you know how we had for the electronic structure, we could expand or fold out the band structure. The same thing here. You can expand that out there into the extended zone plot, if you like. But as I said before, things are normally presented just in the first Brillouin zone. And if we have here that the spring constants K1 and K2, kappa 1 and kappa 2 become equal, then what happens is this gap closes, okay? As you'd expect, because you have to get the same result as if we had exactly a single chain of atoms connected with the same spring constant. So that's illustrated here by the purple curve. But we still had 2 atoms per unit cell. So in real space, lattice vector was like 2a, if you like. And so in reciprocal space, reciprocal lattice vectors become smaller. But the overall shape is exactly that for the one-dimensional chain. Okay, let's just kind of summarize a little bit. So with the one-dimensional chain, the atoms just move in one dimension, okay, as you'd expect. We have, if there is one atom per cell, we get one mode. We only get the acoustic branch, okay, and it goes to 0 at k equals 0. It always has this same shape, okay. If we have 2 masses per cell, which we just did, for any given value of k vector, we get 2 modes because we get 2 bands now, okay. We get the acoustic, as we saw, and the optical band. If we want to extend to m atoms in the unit cell, we will get m modes per distinct value of k, okay. So if you have m atoms in your unit cell, at a given K point, you will have m bands. Okay? So now let's think about a three-dimensional solid. Instead of just having 1 degree of freedom, the atom can obviously move x, y, z. So there are 3 degrees of freedom. Okay? So what you actually get always is 3 different acoustic modes. Okay? They always look like this, and there's 3 of them because you've got 3 degrees of freedom now. One of those acoustic modes will be a longitudinal, and 2 are called transverse acoustic modes. So what about the optical? You will always get 3n minus 1 optical modes because you know you get 3n modes, and if 3 of those are always acoustic, then you will get 3 times n minus 1 optical modes. So this is important sort of formula, if you like, to keep in mind. So we look at some practical, realistic. Yeah.
What is the
Minus 1. Oh, yeah, because we get, remember when we had the one-dimensional chain, when we had n atoms, we had n modes. For the three-dimensional system, if we have 3 degrees of freedom, we have 3n possible modes. Now, the acoustic always has 3 of those modes. Okay, so we only have n minus 1 times the 3 left, and they all go into the optical. The acoustic always got 3. This shows a real sort of calculation for aluminium. Aluminium, remember how many atoms per unit cell it has? Just 1, okay? So, and it's faced into cubic, as drawn here. This shows you, you know, your Brillouin zone that you're sort of familiar with now. And just like the electronic structure, you can plot out the modes or the dispersions as you go in K-space, okay? So we do the same thing. We can plot out the modes as we go along lines in K-space. And what we see is the 3 acoustic modes for aluminium. Okay, because there's just 1 atom per cell. We always get 3 acoustic modes, so that's what you get for aluminium. What about diamond? What would you expect to see for diamond? Okay, we can first of all see we're getting acoustic and we're getting optical branches. How many atoms per cell does diamond have? 2? Yeah, it's got 2 atoms per cell. We get 3 branches for every atom per unit cell. Okay, so we've got 6 branches. 3 are going to be acoustic, and the rest of them will be optical. If you want to use the formula, 3 times n minus 1. N, number of atoms, 2. Minus 1 is just 1 times 3 is 3. Then let's count them to make sure. 1, 2, 3. Acoustic, and then 1, 2, 3 optical. Over here, it looks like there's just 2, but they're actually, one of those modes is degenerate. So when you have a solid, it's always helpful for you to think about your Bravais lattice and think about the basis, think about how many atoms you have per cell, and then you can get a good idea at least of what your phonon dispersions should look like. Finally, yeah.
I just have a little question.
Yeah.
You know when we calculated the structure factor?
Yes.
Structure factor is equal to the structure factor of the lattice multiplied by the structure factor of the basis.
Right.
But my question was, if we have an atom which is part of the basis but on a point of the Bravais lattice, is it counted 2 times?
Yeah. Yes. So it should not be counted doubly. It should be, for example, Yeah, if you've got, say, like diamond is such an example, I guess. It has, well, let's take another example. Yeah, so you define your Bravais lattice for the FCC, HCP, or whatever it is, and if you've got a simple cubic, just like we had for aluminium, that only had one atom per cell. So your basis is one atom. It's still called one atom. So if you have a structure that's made up of a face-centered cubic, but then it's got atoms within the cell, say it's got another atom in the unit cell, your basis would have two atoms. That one that defined the FCC structure.
So the atom which compose the bases are the atoms of the conventional cell.
They are the atoms that may sit at the origin of your Bravais lattice and any other atoms that are inside that unit cell. Yeah, all added together. Yeah. I just finished off with one slide. We're a little bit ahead of time. I just want to show you more of a state-of-the-art kind of results that look sort of more sort of what one gets if you look at real materials. This, for example, is titanium carbide. It's a flat structure. It's actually has a little bit of rumpling in it, but at the top there, we look and see how many atoms per unit cell it has. We can see it's got 3 here and 3 here, so it's got 6 atoms per unit cell. So we can think about how many modes we should expect. We know that there will be 3 acoustic, and we know the other modes should be 3 times n minus 1, where n is the number of atoms, so that's 6. 6 minus 1 is 5, so there should be 15 optical branches. And you can kind of count them all, and you can verify that indeed you do have 15 of these optical branches. Another important thing, remember how when we had the electronic band structure, we could also plot the density of states? You can do exactly the same thing for phonons. These are the bands, your phonon dispersions. These are the corresponding density of states of phonons. And what you can see is just like for the electronic structure, there will be peaks where you have flat bands. So you will have peaks where the gradient of the dispersions are low. Okay? High density of states, low dispersions of the band. Over here you can see a lot of flat bands, and we get quite some big peaks here. And this is the equation that governs it. I didn't bother to derive it, and you don't need to know how to derive it, but it's in, you can find it in Ashcroft and Mermin, or you can find it in that Oxford Solid State Basics, but I didn't want to bother going through it. But I do want to show you that it's formed just like for the electronic structure. Remember, for the electronic structure, we described it as being proportional to the inverse of the gradient of these bands. It's the same thing here. In this case, it's not written as 1 over the omega decay. This is just turned up the other way. But so this is a very nice sort of relationship between the bands, and you can understand that because you will get a high peak because there are very many discrete K points here that can contribute to the density of the phonon states to get the peak. What people can also do in the research is to break down the total density of states there, this one, into the contributions from the various atoms. For example, if we look at this peak here, it's due to a carbon atom, and you can actually also see it's got little tiny arrows on these carbon atoms pointing outwards, and so this indicates which way these 2 atoms are moving, and that gives rise to this density of states here and for this high frequency band. And similar, like the green, for example, that's due to titanium atoms in the cell. Let's have a look. Green one, titanium here. It's got a little green arrow going up and down. So this peak is due to this mode of vibration of the atoms. Okay, look, I think I'm going to stop there. I haven't prepared any more. That finishes the phonons. That's all you need to know for the phonons. And next week we'll start with semiconductors, okay, doping defects and, yeah, things like that. I should say I'll try and get assignment 2 up for you maybe this weekend, okay, so that you have maximum time to work on it.